Okay, now we want to start looking at the topics of geometric optics and image formation. And to start, we're going to look at the issue of mirrors. And we're going to focus specifically on the curved mirrors. Okay. Now, there are many different ways to construct a curved mirror, and you can curve or you can mirror either surface, the inside surface or the outside surface. But you can have a parabolic mirror, you can have a spherical mirror, and the mirror can be a large sphere, it can be a part of a small sphere. Um, in point of interest, most of your optical telescopes that are reflecting that use mirrors, they're going to be parabolic in nature. And a lot of the mirrors that are used in cosmetics, beauty, healthcare, those kinds of things, security mirrors, and those types of things are typically going to be spherical in nature, either what we call concave if the inside surface is mirrored, or convex if the outside surface is mirrored. So as an example of a convex mirror would be like a mirror posted either in public or in a store. And the reason that convex mirrors are used in this case is because it gives you a very wide field of view because the rays come in from different angles and it can catch more rays from different angles. So it can reflect the rays at wider angles, yet still. And as a result, you can see a very wide field of view from the reflected image. So this is one of the reasons why they're useful. But as we will see, they actually lead to a reduced image in size. So this is why, and your mirrors on your car, your rear view mirrors on either side of your car are typically going to be slightly convex, ever so slightly. So this gives you a wider field of view of what's going on in the lanes around you, but it also leads to a reduced size in the cars that appear in your mirrors. And this is where the famous objects are bigger than they appear, that shows up on many car mirrors. We're going to focus on the large spherical mirror. And to start, we're going to look at the concave type mirror um, and its properties. So, with that in mind, what we're going to do is imagine I have an object, whatever that object might be. It can be a candle. I like to think in terms of candles when doing this kind of analysis. And so, a candle, if you will, a candle is going to, I forgot to hit that button. A candle is going to give off light in all directions, right? And so some of these rays are going to follow the paths of these specific rays that allow us to actually determine where the reflected image is going to be and what its properties are going to be. But to start, before we actually look at these specific rays, we have to understand what's going on with the mirror itself. So when we have a curved mirror like that out here, right? So this is the mirror out here. I'm not going to try to draw the whole thing. You get the idea. This is the mirror, okay? Um, since it's a spherical mirror, or at least a section of a spherical mirror, the sphere is going to have a center C. So that's what this point in the middle represents. That is the center of curvature. Halfway between the center of curvature and a point on the mirror itself is called the focus. Okay? That's why we use C and F. Very original. Okay. Now, if I slice my mirror in half with a horizontal line here, so this horizontal line here that slices the mirror in half, this is what's known as the optical axis. Okay. And you can think of it as the x-axis of a coordinate system if you so choose. But it's the axis that I'm going to put the bottom, if you'll notice, okay, so here's the optical axis here. The bottom of my object is on the optical axis going upward, and the bottom portion of the optical axis is empty, okay? And again, a candle is emitting rays in all directions. Sometimes the rays will just happen to be of a special direction. And these directions are, if you have a spherical concave mirror and you have an incoming incident ray, and that incident ray is parallel to the optical axis. So this ray is going to be parallel to the optical axis. When that ray hits the mirror, it will get reflected through the focal point. Okay? When you have a light ray coming from your object and it goes through the center and it hits the mirror, it will then get reflected right back up along that same direction. It hits the mirror at a point where the curvature is just right to send that ray right back up. And where these lines cross, this is where your image is going to be. Okay? And since the image is below the optical axis, you see an inverted image. Okay? You see an inverted image. There's a third ray, and that third ray, that diagram doesn't show it. Let's see. None of those diagrams seem to show it all that well. So we will see if I can draw it. But in any case, if you have a ray that is initially going through the focal point, it will hit the mirror at such an angle that it gets reflected parallel to the optical axis. Okay, so you technically only need two of these rays, and technically this ray needs to be going through the optical axis or through the focal point. Technically, you only need two of these rays. Where they intersect is where your image is going to be. And then you can say a number of things about it. Okay, so first things first. If your image is above the optical axis, now I'm speaking generally, not just in this particular case where our rays are coming in like this. What I'm about to say is generally true. Okay, so if your image is below optical axis, your image is inverted. You see the image upside down. Number two, if I were to measure the height of the image, okay, and if I were to compare that with the height of my initial object, so I'm going to label the height of the object h naught. I'm going to label this the height of the image. Okay, then the magnification is going to be equal to negative hi over h naught. So this is how much larger or smaller your image is than your object. Number three, if your rays physically converge, this is what we call a real image. If your rays do not converge, if your rays do not physically converge, this is what we call a virtual image. Okay. And again, you only need two of these rays. And also, so for example, in fact, let me see if we enlarge this some. So up here, we have a situation for a concave mirror, and this is when the object is beyond the center point. Okay, so your image, your object can actually be anywhere. You can put your object anywhere. But when your object is beyond the center point from the edge of the mirror, this will generally produce a inverted real image. Okay, this will produce a real and inverted and a smaller image. So your magnification will be less than 1. And by the way, the minus sign in the equation for the magnification, this minus sign right here, what that means is that if the minus sign survives, then that means your image is inverted. And if the minus sign does not survive, then that means that your image is upright. Okay. And so, with that in mind, so here we can see the three rays. The first ray comes in parallel to the axis, gets reflected through the focal point. A random ray, this fourth ray, the really faint one, hits the mirror at the point along the optical axis and just simply gets reflected at the angle that it came in at. The ray that goes through the focal point initially then gets reflected parallel to the optical axis, and the ray that goes through the center of curvature then gets reflected back up. And all of these will converge at the point where the image is located. Okay. But when I have a convex mirror, we can see that a ray coming in parallel gets reflected back up and out. And rays coming in that hit the vertex of the optical axis in the mirror get reflected back out. So this is a case where the rays are actually diverging. So your rays are not going to physically converge. But what happens is, if you extend the reflected rays back into the concave region, you can show how the rays would actually appear to converge, and your object will be upright, right? So this is how you get an upright image, but because the rays physically did not converge, this is going to be a virtual image. And the object is located on the opposite side of the mirror, so that's why the H naught would get a minus sign, or HI would get a minus sign, sorry. So with mirrors, when your image is on the same side of the mirror, HI is going to be positive. When it's on the opposite side of the mirror, HI is going to be negative. And so this particular image is going to be virtual, upright, and a magnification of less than 1. Okay, this image up here is going to be um, real, inverted, and a mag less than 1. So your magnifications are really going to be dependent on where your object is. Okay. Now mirrors have a formula, right? Mirrors have a formula. And that formula is if I let my position of my image be P, okay, and as measured from the mirror, okay, so P is going to be this entire length. C is the center of curvature. F is my focal point. The equation for mirrors is going to be, I need to define where my image is. So I'm going to let my image be P prime. Okay. So the equation for mirrors is 1 over the focal point, or technically 1 over what we call the focal length. The focal point is a point in space. The length is the distance from the focal point to the mirror. Okay, so I really should be very specific. So 1 over the focal length is equal to 1 over the image or the object distance plus 1 over the image distance. So if you know 2 of these 3, you can get the third. Okay, if you know 2 of the 3, you can get the third. And if you get a positive number, then your object is on the same side of the mirror. If you get a negative number, your object is on the opposite side of the mirror. And that means that then HI will then also be negative when you plug that into the magnification equation. You can also get your magnification from here as well. Your magnification will also equal negative P prime over P, okay? So these two equations are the same. So what actually happens when you're further from the center point, you're generally going to get, for concave mirrors, you're going to get real, inverted, and reduced magnification. If you put your image, or your object rather, if you put your object in between the center of curvature and the focal point, okay, let's see what happens here. Well, I would have something come in parallel and it gets reflected through the focal point. I'm going to have something go through the focal point and it gets reflected out here. So what you're doing in that case is your image is still going to be inverted, but it's going to be magnified. So you're going to see a magnification larger than 1. It's going to look bigger. So this is when when you bring things closer and closer to a mirror, you'll notice that something happens if it's a concave mirror. When you bring something closer and closer and closer to a concave mirror, you'll notice that the image that you see in the mirror starts out very small and inverted, and as you bring the object closer, it gets larger and larger and larger and larger. Then something peculiar happens. Okay, something very peculiar happens when you bring your image P to the focal point, because then you have 1 over F would equal 1 over F plus 1 over P prime, but you can't have that. Or you can, but that means that 1 over P prime has to be 0. That means P prime has to be infinitely large. 1 over infinity goes to 0. This is where your image gets really, really blurry. there is no defined image. Then, when you bring your object in front of the focal point, then you get images that are enlarged, they're upright, and they're virtual. Okay. And so as a result, you see something that's bigger, but the rays aren't physically converging to get there, and your image is therefore going to be virtual. So let me see if there is an example of this. No, it immediately goes into lenses. So in the next video, okay, in the next video, what we'll do is I'll show an explicit set of examples for a few different types of these situations with mirrors, okay? And then after that, we will get into the lenses, and then we will start in on the issues of diffraction and um, interference, okay? So we will see you in the next lecture.